Hello everyone, welcome back. Today we're hitting section 3.6 on related rates. This section really is based primarily on the work we did in the last couple sections. It's just chain rule and implicit differentiation, only we're looking at some application problems. So really the only different things we'll be doing this time is if it's a word problem, make sure you answer using a complete sentence. Put units on your answer as well. Aside from that, we'll just jump right into applying what we've learned in the last two sections. So we'll start with having a circle with radius of 10 feet. And let's say we are increasing the radius at a rate of 2 feet per minute. So what we want to know is how fast is the area changing? So for this one, they're relying on us to sort of remember our basic geometry facts. So the area of a circle is just pi times r squared. Remember, pi is not a variable, pi is a constant. So the idea is we're changing with respect to time. I believe we used this abbreviation before, WRT, with respect to. That's a common mathematical abbreviation. So change with respect to time. So we will differentiate both sides, treating time t as the variable. Well, the area is going to change over time since we're changing the radius. That's changing the size of the circle. Its area is changing with respect to time. So we'll differentiate the other side with respect to time as well. So left-hand side, derivative of a is 1, and we are differentiating with respect to a different variable than a, so we do have to attach a dA dt. Our other side, differentiating pi r squared, would be 2 pi r now to the first power. We generally wouldn't write the exponent of 1. If it helps you, go ahead and write it. Again, we differentiated with respect to the variable time, different variable used here, so we also have to attach a dr, lowercase r here, dr dt. So just a little bit of simplifying, and then we get to filling in what we know. So change in area with respect to time, dA dt, is 2 pi r times dr dt. Change in radius with respect to time. So change in area with respect to time, that's the thing we're looking for. We don't know that yet, so that stays as dA dt. 2 is a constant, pi is a constant. The radius, at the moment, the radius is 10 feet. dr dt, the sign on that depends on what we're doing, if we're increasing or decreasing. We are increasing, so it's a positive change at a rate of 2 feet per minute. So times a positive 2. So our units on here, our radius, remember, was in feet. Change in the radius with respect to time was in feet per minute. So notice this will end up as square feet per minute, and that does make sense for a change in area with respect to time. Area would always be in square units. So dA dt. So we have 2 by 10 by 2, so 40 pi square feet per minute. And we just toss that into a sentence. So the area is, this is positive, so we'll say increasing. If it were negative, we would say decreasing. Your author occasionally also throws a decimal approximation to that on there. I would prefer just the exact answer. We don't need the estimate on there as well. Okay, so next problem we'll look at a plane passing a tower. You'll get to see some of my beautiful artwork here. All right. So we have a plane. It's traveling at an altitude of 4,050 feet. So here is our beautiful airplane. And here's our ground below. And we have an altitude of 4,050 feet. So our plane flies directly over a 50-foot radar tower. So there's another piece of lovely artwork for you. So this is a 50-foot radar tower. So the plane flies over it, goes directly overhead, and let's say it's traveling at a speed of 500 miles per hour. And let's say we let it go another, what did I pick? 3,000 feet. And we want to know the speed at which the plane is moving away from the radar tower. So in other words, we want to know how fast this line segment is changing. Well, since it flew directly overhead, that was nice of them, we get a nice, neat, pretty right triangle. So here to here is 3,000 feet. From the ground to the airplane when it flew directly overhead was 4,050 feet, but our radar tower happened to be 50 feet, and so we have 4,000 feet for this leg. Drawing is obviously not quite to scale here. So if you're thinking Pythagorean theorem kind of thing, we can call this side A, this one we'll call side B, and the hypotenuse is our C. So by our Pythagorean theorem, A squared plus B squared is worth C squared. So 3,000 squared plus 4,000 squared is worth C squared. And do the math on that, and we get C is 5,000. So our airplane just happened to have made us a nice, neat, pretty 3, 4, 5 triangle scaled up. So we know the values of A, B, and C. We want to know how fast C is changing. So again, this is now differentiating with respect to time. So I'll differentiate the left side with respect to variable time, which means then I also have to differentiate the right side with respect to time. So derivative of A squared is 2A, and if we were differentiating with respect to A, we leave it there, but we're differentiating with respect to a different variable, so we have to attach a dA dt. Same thing happens to our next term, so 2b times dB dt. equals 2c dc dt. Now, if you'd like to work with smaller numbers, we can divide by 2 on both sides, and a dA dt plus b dB dt is c dc dt. And then we fill in what we know. All right, so A, we do have a value for A. A is 3,000 in feet. dA dt, it's traveling at 500 miles per hour, and that horizontal distance is increasing since we're going this way from the point when it was directly overhead to the point later on. We're moving that direction, so it's increasing, so that's a positive 500. B is our 4,000. Since we're only interested in the top of the tower, not all the way down to the ground. dB dt. If the plane is flying level, it's not changing at all, that would be a 0 then. So they'd have to tell me something else in order for this to be a non-zero quantity. They'd have to say the plane is gaining altitude at a rate of blah, 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 or losing altitude at a rate of blah, blah, blah. If they don't tell us that, we're going to assume it's flying nice and level. All right, C, we figured out C to be 5,000. And dC dt, that's what we want to know. How fast is the distance between the plane and the radar dish changing? So that stays as a dC dt. So at this point, we can treat it almost as if it were just a plain linear equation, even though this is really a differential equation. So a little bit of simplifying. So 3 by 5 is 15, and I have, let's see, 3, 4, 5 zeros on there. So 1, 2, 3, 4, 5 zeros. Anything times 0 is 0, and equals 5,000 dC dt. So 1,500,000 is worth 5,000 dC dt. And we just divide both sides by 5,000. So dC dt. So let's say 5 and 15 will go 3, and then 1, 2 more zeros, so 300. So the distance between plane and radar dish is, and again we'll say increasing or decreasing. This was positive, so increasing at a rate of 300 miles per hour. All right. So let's see. So next up, a famous ladder problem. So I'm going to give you the basic setup, try it out, pause the video, and then go ahead and play the video when you're done trying it out, and we'll go through it together. So we have a 25-foot ladder, and we're going to lean it on a building. So there's my beautiful drawing of a ladder. There's our building. We're going to assume our building is a nice, neat vertical building. And the base of the ladder is 15 feet from the base of the building. So on this problem, excuse me, we are pulling the base of the ladder away from the base of the building. let's see, how fast do I want to do that? We'll say 2 feet per minute. Okay, so we've got the ladder leaning on the building. I'm pulling the base of the ladder away from the building and give you the speed that's happening. And what we want to know is how fast is the height of the ladder on the building changing? In other words, this side, how fast is that changing? Okay, so go ahead and pause that, give it a spin, and we'll finish it together. Okay, welcome back. So like before, we'll just go ahead and start labeling things. So we'll just make our sides A and B. If you labeled yours B and A, doesn't matter, we'll get the same thing. Hypotenuse does have to be your C. All right, so same deal as before, right triangle, Pythagorean theorem. Then A squared plus B squared is C squared. So 15 squared plus, we don't know what B is yet, B squared is 25 squared, so 225 plus B squared is worth 625, so B squared is 400, so B would normally be plus or minus 20. We're above ground, not below ground, so we'll hang on to the positive 20 only for this guy. And then we differentiate as before with respect to time. So 2a dA dt plus 2b dB dt is 2c times dc dt. Again, if you want to factor a 2, go ahead. So a dA dt plus b dB dt is c dc dt. And then we fill in what we know. Okay, so a, my A and your A might be different depending on where you put the A and the B in this one. So my A is 15. dA dt, the distance between the base of the ladder and the base of the building, I'm pulling the base of the ladder away from the building. So I'm pulling away from the building. If the ladder's being pulled away, this distance is increasing, so this is a positive 2 in feet per minute. So B, we figured out B using just our basic Pythagorean theorem there. dB dt, that's the thing we want to know. How fast is the height of the ladder against the building changing? We don't know yet. So C is 25 feet. dC dt, if it was a 25-foot ladder at the start of it, me moving it around is not going to make it something other than a 25-foot ladder, so dC dt is 0. The ladder is fixed. Me moving this pen around is not changing the size of the pen. Similarly, a ladder would not change height. So a little simplifying and solving, again, pretending this is a nice, neat little linear equation, one variable. So 30 plus 20 dB dt is worth 0. So 20 dB dt is negative 30. So dB dt is negative 3/2, or negative 1 1/2. Hopefully it makes sense to you that that is a negative number. If I have a ladder leaning against a building and I start moving the base of it away from that building, the height of the ladder should be dropping. If I start pushing the ladder closer to the base of the building, then the height would be increasing. So it should make sense this guy is a negative number. So then we just throw that into our answer sentence. So height is This is negative, so decreasing at a rate of 1.5 feet per minute. All right. There's a couple of our triangle problems. So next up, we'll take a look at a business application. So R of X, revenue, for this problem, 200x minus 3x squared. And C of X is going to be 500 plus 40x. So here, X is units sold. We'll say made and sold. R is revenue. And we'll say thousands of dollars. And C will be then, of course, cost in thousand. So a little bit of other information that they'll give us. When 20 units are sold, rate of change in units sold is an increase of 2 units per week. So we'll start with the change in revenue. So we know that R is 200x minus 3x squared. And we're differentiating with respect to, again, time. So change with respect to time, and the revenue is change with respect to time of the other side. So derivative of R is 1, and we multiply by dr dt. Derivative of 200x would usually just be 200, but again, we're differentiating with respect to something that isn't x, so we also need a dx dt. Similarly, on the next term, minus 6x times, again, dx dt, since we were not differentiating an x here. So then we can just kind of plug in what we know. 1 times anything is that anything. We don't know the change in revenue yet, so we'll keep dr dt. We'll hang on to the 200. Dx dt, increase of 2 units per week. Increase means positive, so positive 2 minus 6 times 20 units sold per week, so x is 20. Dx dt again is 2, same with this one. So dr dt, we have 400 minus 12 by 22, 40. So dr dt is 160. That was a positive, so the revenue is increasing at a rate of, remember that was in thousands, so $160,000 per week. So see if you can repeat that with cost. Just to make things a little easier, I'll copy the original cost back here, and we'll write it just in C equals notation. We'll just sort of mentally know it's a C of X. All right, so same conditions, find the rate which the cost is changing. Okay, welcome back. So differentiating both sides with respect to time. So 1 dc dt or just dc dt. Derivative of a constant is always 0. Derivative of 40x usually would be 40. But again, we also have to attach our dx dt since we're not differentiating with respect to x. So dc dt is 40 times dx dt, if you remember the conditions from the previous page, increasing by 2 per week, so positive 2, so that would be an 80. So the cost is increasing at a rate of $80,000 per week. So don't forget your units on there. That is the ugliest dollar sign I've ever made. $80,000 per week in increase. Now they could also ask us about profit. Remember, profit is just revenue, money coming in, minus cost, money going out. And if we differentiate both sides of that, 1 times dp dt is just dp dt. Derivative of r is 1, and then times dr dt. Derivative of negative c is negative 1c times dc dt. And I can write it with or without the 1. So we can also figure out the change in profit pretty easily from this. So dr dt, we remember that from the previous page. Dr dt was 160, and that was in thousands. dc dt, so it's 80,000. So the profits are, since this is positive, increasing at a rate of $80,000 per week. Okay, so that should be enough information to play around in our applications. So as far as problems to try out, 3.6 if you're in the new edition, 1 to 29 odd, 33, 35, and 47. If you're in the old book, let's see, 1 to 29 odd, 33, 35, and 39 would be sufficient. Okay, if you have any questions, please feel free to get in touch with me. Otherwise, stay safe and hope to see everyone again soon.